Today we're going to talk about mass spectrometry, something near and dear to my heart. We'll go way to the end. We could do a little quiz as always. Quiz 3. Lab 4 planning, I want to talk about that tonight. So there's lab Monday and Tuesday. It's open lab. I'm going to be there. The TAs are skipping out. So I'm going to be there Monday and Tuesday. And if you're going to come for one of those days, come to your assigned lab. Okay? You can't come on both days, but don't come on a day that's not your assigned lab if you're only coming for one, because sometimes that might get a little more congested. You should all have all the supplies and reagents you need identified. Okay? So there's no surprises. And that means a clear to complete list that you can talk with the TAs about. So there's no surprise, because we don't want to come scrambling for something next week or the week after, even worse, and we don't have this, Dr. Lewis can have it, we can't find it. Okay? That's very important. So otherwise, because if you come up with short of something, it will be a planning deficit on your part, not our part. So all supplies and reagents identified and obtained. Okay? If you don't have them, make sure you have a plan for getting them. If you're not sure what that plan is, talk to me. And it's very important in this process, if you haven't done some of the things you're doing, to have the plan where you visualize, each step and what's going to be done, and you have something written out, and you could be asking, what do I need to do this? What do I need to do this? What do I need to do this, right? So sample containers to analyze samples in, or whatever it may be. You want to know that you have to have stuff. You may not know exactly what it is or where you're going to get it, but you have to make sure you know you need it. Need something that you can then ask and get clarification on. Scheduling of instrument time. So what's the mix here? So far, I know you and Austin are doing AA, right? Who else is hoping to do flame AA? Anybody else that's here? No? Okay. Ion chromatography, just you guys, right? Atomic emission spectroscopy, 1, 2. Okay. You guys are, UV viz, right? UV viz, that's you guys. That's actually, it's 2 there, right?
Yes.
1 and 1. 2 groups. Okay. So we have this instrument. That's not a bottleneck. We have this instrument. It is a bottleneck, but there's only one group doing it, so it should be okay, right? As long as you plan, so of course. You know that for this instrument, that it needs to be warmed up and stabilized, right? And so the TAs aren't coming in ahead of time to do that. That's something that you would be doing, planning on, right? Okay. And making sure we have plenty of value in all those things. This is pretty straightforward. There's no issue here. The atomic emission spectroscopy, you guys that are doing this need to contact Rob Franks and say, I want to schedule a time. And this is pretty flexible. This is not flexible. And the way this works for this instrument is you're going to say, I'm going to come in with my samples at 2 p.m. on this day. You coordinate that with Rob. You don't tell him when you're coming. He tells you when you're coming, right? And so you come and say, when are you available? And he'll sign you up on the sign-up sheet, and then you come there ready. Because if you're not ready, then he's not kind of hanging out, right? So you come there, and we'll make sure we interface so that your samples and your standards, your blanks are all organized and ready to go. And you have that window, right? And it's like an appointment to go get your driver's license or something. So you want to make sure you contact him, and you want to anticipate when you're going to be ready. So if you're going to say, I'm going to come do my analysis the Wednesday after Thanksgiving, then that's the deadline you work towards. And come hell or high water, you make that happen, because a lot of times things fill up. So I'll make sure of that. So it's, I think there's 4 groups, right? 1, 2. Wait, what are you guys using?
We're doing AES.
AES? So
the mass.
you got 1, 2,
3.
1, 2, 3, right? Was there one more? Some is that here? Maybe just 3, all right. Okay, all right, so Raphael, you know what I would just say, that you can feel in a way about that, but schedule. Okay, so we're all on board, everything's looking good. Everybody's turning their lab 3, right? Yes?
What is his email? Or do we just go there and talk to him? Or
No, you can email him, yeah.
What is his email?
I don't remember, I think it's marcam@ucsc. 95% sure that's it, but I'm not 100% sure. And so, when you email him, if you have any communication with people outside our group, something like this, CC me. Okay. Okay. So everybody's turned in their lab 3 reports, right? So we're all good. So now we are, on this big continuum of effort over time. We went like this,
I think so.
and now you're right here.
Yeah.
Okay,
What's
so
the
now, in my opinion, the most significant amount of effort in terms of all the things that lead up to, you've just crested.
Yay.
And from here on is when, if you had another axis here, in my opinion, for fun, then we'd be going like not much fun, and now it starts becoming a lot more fun. And it's largely because working on this final lab where you do everything, you conceive of it, you have a question, you make it happen, you go out and get the samples, all those things is all on you. I mean, you're driving that, and that, in my opinion, is what is the most rewarding. And you will come and do the presentation on the Thursday or Friday, 2 weeks after you come back from Thanksgiving, and it'll all be about what you've constructed and what you found. And 99% of the time, it's really fun, it's really rewarding for students to go through that process. And it's cool to see what people do, because people are really creative. And I think in every case, this is always the case, but in every case, with all of you, all the questions you're asking are questions that I think are worth answering, that I look forward to what the answer is. Okay, so today I'm going to talk about mass spectrometry. Some of you, Rob, so what did Rob tell you, the group that went in, the Monday, Wednesday group, about the demo on Wednesday? What did he do? He talked to you about the OES, I know that. Then what?
He kind of went over a little bit of mass spec on what it did, but not really as much. Yeah.
Really? That's so mass spectrometry, I think, is, in this class we focus a lot on elemental analyses, right? Largely because of the instruments we have available to us, and small molecule analysis. And when it comes to elemental analyses, there's no other methodology that I think is more powerful, probably more widely used, both in research, basic research, as well as in applied sciences, than mass spectrometry. And in the chemistry department, there is a really well-furnished molecular mass spectrometry facility that has several different mass specs, and I'll talk about those today and later. Those kinds of technology where you're measuring molecules that get fragmented, and you're looking at a fragmentation spectrum to identify the molecule, typically, right? The kind of mass spec we'll focus on today is referred to as elemental or atomic mass spectrometry, where your goal is to measure individual ions of a particular isotope or a particular element. And this is just sort of the examples of different kinds of mass spectrometers. Now, just like when we started learning about the ICP OES, the inductively coupled plasma optical emission spectrometer, which some of you saw this week, in all these kinds of methods, there's always sort of a hyphenated name to them, where the first part is referring to how the sample is sort of processed and put into some state that can be measured. The second part of the acronym or the term is referring to how the platform is actually performing the measurement. So for ICP mass spectrometers, it's the same kind of inductively coupled plasma we talked about already, but now we have a mass spec on the other end rather than an OES spectrometer, right? There's other ways that we can introduce ions as atoms into the mass spec, and one is via a spark source upfront system. I'll talk a little bit about. Or glow discharge. These are much less common, right? elemental circle analysis, laser ablation. I'll talk about all these examples, and all these have mass spec at the end, and just different ways they get the analyte sample into the mass spectrometer. Now, one big difference when we think about this transition, it's probably obvious, but I want to make sure it's clear. When we transition from the methods we've been using and talking about so far, like atomic absorption and atomic emission, those are all, of course, optical-based methods, right? And that is, why we call them optical, because we're dealing with light, right? We're measuring the absence of light, or we're measuring the presence of light, right? And mass spectrometry has nothing to do with photons. Okay? Mass spectrometry is we're actually measuring atoms, right? Isotopes that have been ionized and then steered down the mass spectrometer to hit a detector. So we're doing nothing with light. So we're distinguishing measuring masses of things versus measuring photons that are generated or absorbed by things we what. And there are a lot of great advantages of mass spectrometry. One is, the most important is the detection limits are typically in the parts per trillion, sometimes in some cases in the parts per quadrillion. And so you can measure things that are really, really low in abundance in a sample. And so they're typically, detection limits are thousands to millions of times better than atomic absorption or even atomic emission. And that's necessary for a lot of things we might want to do, like measuring, like in ocean sciences where Rob works, field. A lot of people in that department have made their careers out of understanding the geochemical cycles of trace elements in the ocean. And most elements in the ocean, like copper and iron and all the other elements they may want to measure, are typically in the parts per trillion or lower levels. And so you need very sensitive instruments to be able to measure those, right? And the technology's developed in the past 20 years or so to allow people to do that. So one is that their detection limits are very good. Another very important point that I'm going to talk about in more in a second is the spectra are very simple compared to the spectra we have been seeing in atomic absorption or atomic emission. Okay? And simple spectra are typically easier to interpret. There's a benefit to that, right? One thing that I'm going to talk about on Wednesday that we've taken in kind of some of the work we do in our lab is taking advantage of is that you have the ability to measure individual isotopes. And why would you want to do that?
Radioactivity?
Tell me what an isotope is. I guess you're a chemist. You're
Neutrons?
on the inside.
Yeah, neutrons.
So an isotope is neutrons?
No.
Well, you know, it's different numbers of
I know
neutrons.
what you mean, right? Just want to make sure you're not a long time. All right. So why would you want to measure individual isotopes?
To help you
Some
estimate the age of
isotopes.
certain,
Some kill you, some don't.
Okay.
Yeah, that's right.
like I'm just thinking carbon dating.
Okay. So for carbon dating,
I get the
that's right. So for some of the carbon dating, they measure the radioactive decay of the carbon isotopes. In the more sophisticated carbon isotope dating, they use mass spectrometers to separate carbon 12, carbon 13, carbon 14, and determine ages of things based on the abundance of those different isotopes. So that's one.
same with lead too, right?
Same with lead. That's right. In fact, what I'm going to talk about is the people who originally dated the Earth. Figure out how old the Earth is. How old's the Earth, roughly?
14. 14.3?
What?
No, that's the universe.
Yeah,
How- how- what?
4.53.
Yeah, so it's about four. I thought you just said million. I was like,
No, I said million.
yeah, so it's about 4.6 roughly billion years old, right? And the people that originally determined the age of the Earth back in the 50s used mass spectrometry to look at lead isotopes in meteors compared to the abundance of those isotopes on Earth, and knowing how the decay rates of the lead isotopes coming from uranium or thorium could back calculate how old the Earth core was. Right? And they did that with some of the earlier mass spectrometers that were developed at that time. Okay? So there's a lot of uses that you might want to be able to look at isotopes for. Probably one of the most important and relevant for you that you could utilize right now in this class comes to that issue of accuracy that I talk a lot about. And there's a method called isotope dilution mass spectrometry, where you could say, I want to measure the concentration of lead in these samples, and I don't have any standards, and then there's a matrix problem, all these things. And since lead has 4 different stable isotopes, I can take one of those isotopes, and add it in excess to my sample and measure the isotope that I added compared to the isotopes that were there inherently, and knowing the ratio of those two, I could actually calculate exactly what the concentration of lead is in the sample. In fact, the gold standard for determining accuracy, for determining concentrations of elements in things, is by an isotope dilution method, because you can add an isotope to your sample, and it's like an internal standard we talked about, but even more specific. So there's a lot of advantages to why we would want to measure individual isotopes of a sample in order to characterize aspects of it, accuracy, the measurement or whatever. The problem with mass spectrometry is it costs a lot of money. Is that when you look at the relative cost, the cheapest mass spec that's over in the lab you guys saw is probably about $125,000. The one in the next room over that I showed you is probably about $300,000 or $400,000. So typically they range from $100,000 up to $500,000. And so it's not something that an individual would just buy. They would typically have to get a major research grant to purchase that, as I mentioned. And like all measurement methodologies, there are sources of interference that could be a problem, and there are isotopic interferences that could be problematic. And that is that if we're measuring lead, so one of the lead isotopes, you can get two smaller atoms that can form a complex in the plasma and then travel to the mass spec as a complex of two atoms that may have the same, very similar mass to one of the lead isotopes you're going to interfere from that. I'll talk a bit about that. So the spectra that you generate from a mass spectrometry measurement, of course, this spectra is based on mass. We're measuring mass. And this is an example of a ICP mass spectrometer spectrum from a laser ablation analysis of a rock. And so in the lab here, in a lot of labs with mass spectrometers, they actually have, instead of having an ICP alone, where you have a liquid sample that you have to aspirate into the ICP and then ionize, is that they have a laser. It's upstream of the ICP part. And the laser can ablate samples, or their solid samples, and generate an aerosol of solid, very fine particle dust, then it gets incorporated into the plasma. Right? So it's a way to analyze things. And this is an example of a rock that's been directly analyzed by laser ablation, where you're just ablating off dust of the rock that goes into the mass spec. And you can see it's a relatively simple spectra. Right? And when you compare this mass spectra for things like this is for cerium, compared to atomic spectra, right? You can see how much simpler it is. It's much simpler to interpret than atomic spectra maybe. Okay? And that's one advantage why the mass spectra is sometimes much easier, much more free of interferences, because it's much easier to interpret. Okay, so I want to show this side of your book. I'm only going to show this just to kind of reiterate these different kinds. There's lots of different kinds of mass spectrometers, and basically they're broken down in how are you generating the ion that's going to be flying into the mass spec, and how are you going to separate those masses. Right? And there's a range in costs from the cheap ones, what are referred to as quadrupoles. We'll talk about that. And the mass analyzer is the part of the instrument that's actually separating individual isotopes based on their mass to charge ratio. And the more sophisticated instruments have a magnet, and sometimes they have two magnets, or they have electrostatic, electrical field separator, mass analyzer, and then followed by that as a magnetic, big magnet that separates in a magnetic field. And these are able to separate isotopes to a much finer degree with higher resolution than are some of the cheaper ones. So these are under 25,000, these are 300,000 to 400,000. That's what you get for the money. Okay, so you've seen some of this kind of stuff before. The first thing you have to do in a mass spec is what? If you are separating things based on the mass to charge ratio. So the mass analyzer of all mass specs is based on a field of electrical potential or a magnetic field. So there's some kind of a field that's generated, and within that field, isotopes are going to take a different trajectory of travel depending on their mass to charge ratio. So let's just think now, if you are, what's your favorite isotope? Everybody has to have a favorite isotope.
Carbon.
What? Yeah.
What is it, americium 241, is that it? Oh, yeah, you're right.
All right. Something, now, this is heavy, obviously. Okay. Now, would this go anywhere in mass spec? Is that written?
It's not an island, right? So it's not an
Ion, right? So what is it? Does this get ionized in the divalent cation? So you get monovalent, divalent? Nobody knows? I don't know. So it says a divalent, it's ionized to a divalent cation. Okay, so in order for this to go anywhere in a mass spectrometer, the first thing that has to happen is what? Ionize. You have to ionize it because you have to put a charge on it. If it has no charge, it will go nowhere, right? And then, once it's going, it has a charge, but then to actually be able to separate it from other things, it has to have some, well, I'll just say it has to have a charge, and it has to have some velocity, right? It has to be moving. If it's just static, it's not going anywhere, of course, it can't travel towards the detector, right? So unlike light, that's going to be traveling less photons, these ions of these isotopes have to have a charge and have to have some velocity on them in which to actually channel and steer them into the detector if that's what you're selecting for. So in all mass spectrometers, the front end of it is all about generating the charge, generating an ion. Right? And there's lots of different ways to do that. Okay? And the one way that's most commonly used now in the facility where Rob Franks works is to use an inductively coupled plasma to generate that ion. Once the ion's generated, then this thing has to get into the mass spectrometer, right? Because you have an ICP torch, and the sample's coming out, and it has to get from the torch, coming like this, into the mass spec, which is up that way. And the way it achieves that is by having a number of what they call electrostatic focusing plates, which are just literally slits in a plate that have electrical potential on them. And they line up multiple plates like this. So if I were to redraw this, and I'll show a picture of this later. If I were to have a torch coming like this, and here's the cone of the torch coming out, right here at the end of that torch are a series of plates. And these all have little slits in them. And these all have different electrical potentials applied to them. And the potential applied here is greater than the potential applied here, so that the ion is charged, and you have to set a mass spectrometer up to either accept and accelerate cations, positive ions, or negative ions, right? Because you can't do both at the same time, obviously, because they'll go in different ways, right? So most mass spectrometers are set up to detect cations. And so the electrical potential is set up here so that it becomes increasingly negative this way, and it accelerates that charged ion through these little slits into the mass analyzer. So everybody that gets generated, all the ions in this plasma that have a positive charge, will get accelerated into the mass spec. And then they enter the part of the mass spec that's called the mass analyzer. I'll show all this. And that's where we start selecting for these ions. And selecting meaning I want them to go this way into the detector and not fly off into the side. I start selecting for those based on the mass to charge ratio. And some really smart people have figured out what type of electrostatic field or magnetic field do I need to set in the instrument in order to select for an ion that has a mass to charge ratio of uranium-238 or some other isotope. Right? And it does that. So what we want comes through, and what we don't want just goes off to the side. It stops. So in all cases, we have to have something to generate the ion. In many cases, it's an inductively coupled plasma. Other kinds of mass spectrometers that are in a different floor under the Marine Science Building use electrical heating on a little wire to make it really hot to ionize things. We have to have a way to generate the ion, and then we have to have a means to accelerate the ions into the instrument, the mass analyzer. And that's done using electrical potentials across a number of different focusing plates. Then once they get into the mass spec, they get selected for based on their mass to charge ratio, and then they get detected. I'll talk about all that right. So this just kind of reflects the, really simple box way. This is for your book also, what the basic design is. And, it's the simplest way. We start with something like a liquid sample, and we suck our sample up and we make ions out of it by a number of different ways. Those ions get accelerated into the instrument where they get separated, and then they get detected. It's really simple. And there's one key feature of mass spectrometers, and the more sophisticated the mass spectrometer is, meaning the higher the resolution, meaning the greater ability it has to separate masses that are adjacent to each other. The more sophisticated and higher resolution they are, and more costly they are, the more they rely upon a very high vacuum within the instrument. Okay? So you can see on this case here, one thing, besides some of the other little things they do, one thing that's featured is a vacuum. What happens if we start accelerating ions in a space that's at atmospheric pressure? They bump into oxygen, they bump into nitrogen, they bump into those gas atoms that are part of air, right? And what happens if they bump into those?
You see them.
It deviates their trajectory, right? It deviates their trajectory, and so you don't count them because they hit the side, they're going off. You know? And it's not only do you not count the ones you want, but you end up counting ones you don't want because they're not supposed to get there if they bump into something and maybe establish a trajectory that we can detect it. So all mass spectrometers have different degrees of vacuum systems to generate vacuum within the instrument. And the ones that are really the high resolution mass spectrometers will generate a vacuum that's down to like 10 to the minus 9 torr. Extremely high vacuum. Extremely high vacuum. In fact, the mass spectrometers, when you would load samples in, you would start the vacuum system, and because parts of the instrument have been exposed to the atmosphere and there's adsorbed on the surface just oxygen molecules from the atmosphere, not even condensate, just gas molecules, you have to start the vacuum and come back about 8 hours later for that to finally pump that gas down to its low enough vacuum. And so a big cost of these mass spectrometers for the higher end ones is establishing these multi-stage vacuum systems to pump it down to extremely low vacuum. So if you look at the components then, you got to make an ion, you got to separate the ions based on their mass to charge ratio, you got to measure the ions, and now all of this has to be done under a high vacuum, which is just actually relatively simple from that standpoint. Now, if you look at it in a little bit more sophisticated way, you can say, well, in reality, when we look at mass spectrometers, we have our solutions, a water sample. And then I'm going to take my water sample, depending on what kind of mass spec, or whatever my sample is, I'm going to generate an ions out of that sample. So I've got to take one of these possible methods, and many people would take high-performance liquid chromatography and marry that to a mass spec, and they separate analytes by HPLC and then ionize them. There's a whole bunch of different ways that you can generate a sample that's going to be introduced into the mass spec. Then the thing gets ionized in the ICP, typically, right? Then the thing gets accelerated into the mass spec and then separated by the mass field, mass analysis of the mass spec, and then finally it gets detected and multiplied. So the components are simple, but of the highest, typically of the highest technology because of the need to have very, very reproducible, very low noise types of components which to separate things. So we've already talked about this, right? You're familiar with this. I'm not going to go over this. You've got to get a sample in there. It's a liquid sample. And this very similar approach is used to generate a very fine aerosol in a ICP mass spec as it is an ICP OES. Sometimes it can even be, the parts can even be interchangeable. The torch we talked about, I'm not going to talk about that either. It's the exact same kind of a system to generate an inductively coupled plasma on these ICP mass specs. I'm not going to talk about that. You guys all remember all this? So that's ready to go over it again, is it? So one difference is with the mass spectrometer, unlike the OES on is that we actually have to introduce ions of our analyte, not products of our analyte like the photons of emission. We have to introduce ions of our analyte into the instrument to be focused. And so this is meant to be a sort of a cartoon of what the torch would look like. And the torch is I don't know if Rob showed this. Did he show this? He probably shows in the mass spec. So the torch is focused so that if I blow it up, it's like this, and the plasma is probably coming off like that. Right? And your sample comes out right into the plasma. And then for the instrument, it actually has these sample cone, they call it, and then something they call a skimmer cone, which is shown in the thing, that are impinged right up against the plasma. These are made out of some very special nickel alloy metals. So this extremely hot plasma, which is pushed right up against this orifice, it's about maybe 0.5 millimeter diameter. So it's a very small pinhole, and that's where your sample goes into the thing. So it's got several of these cones, and they have electrical potential. Then it goes to these plates, and that's exactly what's shown here. The sample comes in, it's supposed to be a really small opening, comes in a little bit of vacuum here, comes in a small opening. This is removed, and then it flies into the electrostatic focusing lenses to sort of accelerate and start focusing it. And so one of the challenges with the ICP mass spectrometers was that you needed to generate a very high vacuum, but you need to have a hole in it so your sample can get in, right? And those are sort of contradicting to one another. And so they solved that by having multiple vacuum stages in the instrument, so that this is like a pretty, relatively high vacuum, and then it comes through this space, this is a higher vacuum, and it's easier to maintain through these progressively increasing vacuum stages because the orifice is so small that very little air can actually get in compared to how fast those vacuum can pull that vacuum down. So we generate the ions, they come through, they start getting accelerated, and by the time they get into the mass analyzer, they're moved at some high velocity that is then utilized to help steer them in that electrical or magnetic field. Okay. So the simplest kinds of mass analyzers are things called a quadrupole. And they call it a quadrupole because it's quadruple, which means 4. And there's the 4 poles. You can see exactly what one looks like. They're not very big. And what this device is these 4 metal rods. And on 2 of the rods are alternating DC current. And on the other 2 rods, on 2 of the rods are alternating DC current. The other 2 rods are RF voltage. And it oscillates and the voltage is oscillating between the 2 poles in this axis or this axis. Is oscillating so that when your ion comes in, it's traveling within this electrical field. And the ion, depending on its velocity, which is in part based on its mass, and its charge, it's going to enter into this space between these 4 rods where it has this oscillating electrical field and start traveling down. And the ones that we're selecting against, based on the RF and the electrical potential on these poles that we're selecting against, will bounce into the side of the pole and never make it out of the mass analyzer. We're going to measure it from one of them. And the ones that we are selecting for, because how we set the settings on this quadrupole, travel through and out into the detector. And so the quadrupoles like this are relatively inexpensive instruments, 100, 150,000 or something like that, because their mass analyzers are relatively unsophisticated. And what that means is that we can separate pretty well individual ions, individual isotopes, but we can't separate them to the same degree of resolution we could if we had a much stronger magnetic field. And that's the big difference. For most applications, this works fine. If you wanted to measure lead isotopes, or you wanted to measure uranium, thorium isotopes, this would not be effective. There's a study we did years ago, right after the first Gulf War in Iraq, and at the time they still used a lot of depleted uranium. Speaking of uranium, depleted uranium in the armor-piercing munitions. And so depleted uranium is uranium. Can't remember which one it is actually. Maybe enriched in 238. There's yeah. I think 238 is the heavier, and it's less radioactive. I can't remember how it goes.
Yeah, 238 is the most stable.
Yeah, right. So you guys can tell me. We had a goal of trying to measure depleted, because they would put depleted uranium in these munitions, and that's what they would use to pierce the armor because it was heavy and dense, and when they fired these projectiles at tanks and would hit them, it would vaporize and create such heat that it would melt the steel in the tank, and then they would get inside and blow up, right? Kill everybody. And so they had, at the time, there was a hypothesis that the Gulf War syndrome that a lot of the returning veterans were suffering from may have been due in part to toxicity and poisoning from depleted uranium, because when these uranium munitions would hit the tanks, it would vaporize into these extremely small particles, contaminate the whole area. And all these veteran soldiers were there getting exposed to this dust. And so they had a big program where they were measuring the ratios of uranium in urine and blood of these Gulf War veterans and trying to understand to what extent, one, did they have high levels of uranium in their bodies, and two, was it uranium that was consistent with depleted uranium? And of course, they were interested in that because they wanted to be able to say, I'm sick, it's because of this, and I got it while I was in the military service from the munitions. And so we had a study where we were looking at, for a lot of veterans, developing a method to distinguish depleted uranium in urine samples from all these veterans. And a mass spectrometer like this was wholly inadequate because there's a lot of other interferences for some of these uranium isotopes, as it turned out. And it required using a mass spectrometer, a different one that we had at the time, that allowed us to resolve the uranium isotopes from other interfering isobaric interference that I'll talk about, to actually make the distinction that it was depleted uranium, and it was. It's not what they were getting sick from, but they did have high levels of depleted uranium. So if this is like the Volkswagen of mass spectrometers with a quadrupole, then on the other end of the spectrum is one that's called a magnetic field double focusing mass spectrometer. And we have one of these instruments upstairs where Rob is. And these are about, I think when they purchased this 6 or 8 years ago, it was $750,000. So $750,000. And it was like a state-of-the-art instrument because it had on one end a plasma torch that made it really easy to introduce samples for the ICP. And it had on the other end 7 individual detectors. So you could look at 7 isotopes that you could focus down to the mass analyzer and measure all 7 of those simultaneously in 7 different detectors because you would steer them all in the 7 different detectors exactly. And it's still one of the most sophisticated mass spectrometers available. And the advantage of it is that when you introduce the sample here, just like you do in a quadrupole or the mass spectrometer we just talked about, is when the isotopes that are ionized get in, they first go through an electrostatic analyzer we talked about. So this is the first stage of a mass analyzer. It's not, it's sort of equivalent to the quadrupole, but a little bit more effective. And they put a radius in that trajectory, right? And that radius in that trajectory is there because it's much more difficult to essentially channel an isotope, an ion, across a radius, trajectory radius than it is just in a straight line, right? And so they can steer the things you want through this electrostatic analyzer through some additional focusing lenses, and then ultimately into a very strong magnetic field. And these magnets are probably about this big around, and the flight tube, which is what they call the thing when the ions are going, is something about, measures about like this. So it's really skinny and narrow space. It's under very, very high vacuum inside. And the ions just travel down through these mass filters, successive mass filters, that are doing successfully a better and better job of separating out isotopes or masses that are very, very close to one another. So that by the time they get down here to the detector, you have things that are resolved down to like 0.001 atomic units or better. Right? And that's necessary in many cases to do that. So we already talked about this. We know why particles got to be charged. What's cool about this is thinking, who are the engineers that are figured out under these varying mass magnetic and electrostatic fields, how the ions are going to behave, how they're going to fly down the flight to the mass spectrometer. And they've done this, and they can calculate this, and they can determine for a given mass to charge ratio based on the magnetic field strength and the radius of the trajectory and how rapidly, how fast the velocity of the ion is traveling. They can predict exactly what the trajectory is, and they can use that, and they do that in the programs for these mass spectrometers. That you go in and you say, I want to select for uranium-238, uranium-235, whatever, right? And the instrument then does this calculations for you. It sets the strength of the magnet in the electrostatic mass analyzer it's going to allow you to predict for this, an ion of this charge and this mass, what to set the field at so that it actually reaches the detector exactly as you want it. Right? It's remarkably, obviously, remarkably predictive of that. And this essentially goes over the same kind of same kind of calculations that what people are thinking about right now. Okay. So, why is it important that the electrostatic magnetic fields be stable? What does that mean when I say stable?
Constant.
Constant, right? Invariant over time.
Because if they want the trajectory to go off.
The trajectory would go off, right? And it would be, variable. So, I haven't talked about this, maybe I'll talk about it. It's coming up now. Detectors, okay. So I'm going to come back to this question. Let's think about detectors. So there's two basic kinds of detectors that are used in mass spectrometers. And of course, it's obvious that the big departure from detectors we've talked about so far is that they're actually measuring, physically they're measuring not a property of the analyte, they're measuring directly the analyte, right? It's the ion, it's hitting the detector that's eliciting some response. In ion chromatography, you were measuring a property of your analyte, right? You're measuring conductance. In atomic absorption and atomic emission, you're measuring the photons that were absorbed by or emitted by your analyte. So you're measuring an indirect consequence of the levels of your analyte. And in mass spectrometry, you're actually measuring the individual ion. And so when they characterize an ion that strikes the detector, that equals 1 count per second. So they're measuring a rate of which your analyte ion actually strikes the detector. And they're always expressed in the form of counts per second. In atomic emission spectroscopy, when you, for those of you who do that, the signal you actually get in that instrument is also counts per second, but it's not analyte counts, it's photon counts, right? It's events of photons that strike. In mass spectrometry, it's actual counts of the analyte ion. And so, if you were measuring an isotope, and you're generating ions that isotope, and it's being introduced in the mass spectrometer, flying down the flight tube,